going to get started, and hopefully that the folks that are coming after can actually keep up with us once we get moving. My name is Maulan Byron. I'm an engineering manager at Comcast Cable. Some of the things I'm interested in is basically performance engineering, capacity planning, how you make software scale. Most of you guys who've been around long enough, you know, back in the day, we would do basically the waterfall approach to software development. You know, you do analysis, design, development, testing, and 4 months down the line, you have an application that works, and you've done an elaborate capacity planning model on it, and it works. Everything's great. And about 10 years ago, we had the agile revolution where basically everything is iterate, fast, rapid development, rapid deployment. And if you think about it, a 4-month capacity planning model gets kicked out the door. It doesn't work, it's irrelevant by the time you actually put the thing together and produce some type of scale projection on your system or application. Basically, it's useless because the application's probably changed 10 times by then. So the idea here is, how do you get capacity planning back into the SDLC process, right? How do you get performance analysis in the SDLC process to a point where it actually is valuable? It adds a lot of value to the whole process. It helps people understand and at least start thinking about scale at an early phase within the development process. And I think that's something that's important, especially at the rate at what we deliver software these days. It's something that's critical. So what you're going to learn here basically is an approach as to how you can actually make capacity planning work. So to level set and get everyone on the same page, let's basically describe, what are we talking about? We're talking about capacity planning, and what is it? It is the process of determining the production capacity need by an organization to meet changing demands for its products. And a lot of times folks kind of interchange this with capacity management. You want to read more about it, you can check ITIL. They have a bunch of description on that stuff online on Wiki, and have at it. So this is what we're going to talk about. We all know what it means. We understand the terminology. Great. So a lot of you guys have seen a system like this. N-tiered architecture, basic, simple. You have a client, you have a bunch of application servers that usually gets data from some RDS instance, some relational database. Great. Can you scale something like this? Can you figure out how this thing is going to scale in the future? Can you do capacity planning for something like this? And we all know the answer is yes, right? This is the easiest thing you could actually do capacity planning for. But for most of us, we know our system doesn't look like this. And I think for a lot of you guys, your system is somewhere between that and this guy, where it's probably in the cloud. You have tons of racks of blades, you have network gear, you have shared storage, you know, you have Oracle instances, you might use MySQL, you might have Cassandra, you have Coherent. So a real mush of technology in your system. And the question is, can you do capacity planning on something like this? And the answer is yes, you can. Right? And what you're going to learn here, I'm basically going to show you an approach as to how you can do this, and you don't need a PhD in math to actually be able to do it. So that's the idea here, an agile approach. All right, so what are you going to learn? How to do capacity planning at an agile pace? Using a spreadsheet. What a novel thought, right? Simple spreadsheet. And most of you guys have this stuff on your laptop already. You don't need anything expensive. Plain old Excel or OpenOffice or anything like that. All right, so we're going to talk a little bit about your tool belt. So basically, when you think about tools, when you do capacity planning, you kind of look at it in two major categories, right? You think about stuff that's going to measure or monitor your system, give you metrics from it, and stuff that's going to help you analyze that data, right? So when you think about measurement, you're looking at your basic tools. You could be Splunk. You could be using JMX to capture metrics on your application. If it's Java-based, you can have tools like New Relic, AppDynamics, Dynatrace, Wiley, and a bunch of other open source tools for what you would consider measurement, right? This is how you collect data on your system. And then the next category are the guys that help you do analysis. So Excel, R, RStudio, tools like queuing theory, Amdahl's law, the universal scalability law, things like that, right? Those are the tools that's going to help you actually take this data and turn it into something where it makes sense that you can, quantify how your system is going to perform at a later date at a different scale, all right? So the example we're going to go through here, we're going to actually talk about Excel, and we're going to talk about the universal scalability law. because that's where I've actually done the exercise using those tools on a real system. So we're going to talk about that. So let's get started. So a lot of you guys have seen this chart. It's a basic performance or scalability chart for a system or application. On your vertical axis, you have throughput. And what is throughput for you guys? Think about it like this. It's work done by your system over a period of time. So technically, it's a rate, right? So it could be throughput is transactions per second, requests per second, bytes per second. And for those of you guys who are more interested in hardware, it could be CPU cycles, MIBs, whatever. It's work done by your system over a block of time, so it's a rate. So just remember that when we go forward, just so we level set on what throughput is. At the bottom here, you have scale. And scale, in this case, we're going to focus on scale as being the number of nodes of an application. For you, it could be virtual servers, it could be physical servers, it could be CPUs, all right? So let's distinguish those two things, because those are the two data points you're going to actually need to be able to apply this particular math analysis to your system to determine how it scales, right? So you see this nice curve here, you've seen it. Application scales up as you add more throughput, and as you add more resources below it in scale, and you see a nice little curve where it kind of topples off, or it caps off at the top, and then it kind of slopes off. So we're going to break this down into three main phases. So let's start. Phase one. Most of you guys have tested 1 to 4 or 1 to 6 nodes, and your application looks great. Man, this thing looks like it scales linear. Let's get this out there. And I know a lot of us have found out the hard way, which is phase two. You realize after a certain point, your system actually start getting diminishing return. So you add 20 nodes and you're not getting 20 times the scale as you predicted. Somewhere in between there, you have something that your system is contending on, right? And a lot of us who've done a lot of work with scaling system or capacity planning or even performance testing have seen that often, right? So that's phase two of this curve. Phase three, at this point, your system is literally collapsing on itself, right? You've added a bunch more nodes, and instead of it at least slowing down in terms of the capacity you get, it's actually toppling over. So we've seen that. And this is not a phase, this is just basically to tell you this is your maximum point. So this shows your line where you're at your peak throughput, and that corresponds to a scale point at the bottom, which means that could call that a number of servers or an X number of CPUs. So let's just focus on that. So we're all on the same page what we're talking about here. And now I'm going to show you some parameters that basically describe and dictate the shape of these phases in this curve. So this is a universal scalability law, and these are the two parameters that you basically need to be able to do the calculation. So getting throughput and scale lets you do analysis to get these points. So alpha and beta, we're going to call them, and they basically determine the shape of your curve for your application. So let's just move forward a bit. So what's alpha? Alpha is contention, and beta is coherency. And you might ask yourself, what's contention? What does that mean? How can I quantify that? So think of it like this. If you have a system that returns metadata, that's what it does on something. And your metadata could come from Cassandra, it could come from Oracle, something that stores data, could be a file system, right? Contention basically means your application is bottlenecking on a resource behind it, a shared resource. Simple as that. Coherency, what is that? It's the efficiency you lose when your applications or a cluster basically is trying to keep in sync. That's literally what it is. Efficiency you use based trying to keep things consistent. So let's just level set there. You know what contention is, you know what coherency is, you know which parts of that curve it actually affects and shapes. And remember that, because we're gonna build on that going forward so you can understand how you actually use this stuff to quantify your application behavior and how it's going to scale. All right, so what I'm going to do, I'm going to go into a brief example as to how you actually do this thing in Excel. And further down the line, we're actually going to show you how you apply it to a real system. So let's jump briefly into Excel right quick. All right, so we're going to get a nice little spreadsheet up here, and we're going to work through this spreadsheet. All righty. So what I have here basically is a spreadsheet that, excuse me there for a second. So we have a basic chart here, no points mapped, and some canned data at the bottom. And all I'm going to do here, I'm going to plug some of this data in. So you see here I have measured servers. So at one server, I actually measured a value of 920 transactions per second. Plug that in, nice and easy. At two servers, so this is two nodes of a specific service, we've measured that the service can handle 1,763 transactions per second. Nice and simple. You can measure that, you can do this stuff in performance testing, you can even get it from production. So let me bypass this a little bit, and I'm just going to copy the rest of this data in just to speed this up a bit for you. Drop this in, just going to paste in values here. Boom. So what you just saw there, I have a bunch of macros in there that basically takes this data, it runs a regression analysis on it to basically calculate alpha and beta. And I'm going to explain this a little bit more once we go forward, but basically if you look here, a little bit to the right, you see data points plot. These are just measured data points. What I don't have on this chart yet is what I would consider as the modeled curve. So you don't see this curve. So let's get that data in there. So we're going to simply drag this across a bit, right here. Right? So you see a nice little curve being plot there. Let's play around with this a little bit. We don't want any markers here, so we're going to do no markers, and we're going to take the line and we're going to give it a nice black color. And let's just make this a nice dashed line so it's different from what the chart. So you look at this nice little chart here, you see the blue dots, that's what we measured. The nice dotted black line here shows you what this model tells you your system is going to be, where it's going to project, right? And real simply, you notice, it's telling you somewhere around between 20, 26, to be exactly 27 actual servers or virtual nodes you're going to cap out. Right? So if you think about it, most of us can't really simulate to the point where our system will break. Depends on how large your system is. You're going to spend a lot of money spinning up tons of JMeter nodes or load runner nodes trying to generate enough load to stress your system to a point where you could actually witness this. The idea is this, you want to be able to do this virtually, calculate it, right? So what you just saw is me taking some measured data, plugging it into Excel, a bunch of regression work happens there to generate alpha and beta. And keep in mind, you notice alpha and beta here are basically decimals. I'll explain a little bit how you convert this to an actual unit that makes sense to you. But nice simple example. I have a second service here, and this is also just like the previous service, but slightly different in terms of its measurements. If you notice here, at one node, you see 48 transactions per second. So real simple. You plug it in again, one node, we have 48 transactions per second, plug that in, just like that. We go over and get the rest of this data point. I'm just going to copy this in to speed this along for you guys. I'm going to go up, plug this data in, and we're going to see what this curve for this service actually looks like. All right? Voila. So it's plot that. I'm going to go in here. I'm also going to go and now add the modeled data point in for this service. As you can see, very different curve. Do the same nice little pretty change I made. I'm going to put a line in here. We don't want any markers. Want a nice black line. Add it, make it dashed, so that we can actually identify the 2 points. So you see here, the blue dots, measured value, black line, curve. If you notice here for this service, the characteristics are very different, all right? The contention number and the currency number is very different. The shape of the curve is different. And if you probably look at the measured value, you could see that the service seems to cap out somewhere. The last 4 measurements are basically saying it's not going anymore. It's not going any further, right? And you can see the actual model curve kind of suggests, hey, at a certain point close to that, this service has hit its max. No matter how many more nodes, no matter how much more scale you give to it, it's not going to perform any better, all right? So now that you've seen that, let's jump back to the actual presentation, and so you can see an actual example of what that looks like. Alrighty. So what you see here is basically a finished, full-fledged version of that spreadsheet. And mind you, I didn't make this spreadsheet up, I just modified it. This spreadsheet actually comes from a site of this guy named Neil Gunter, who's the guy that actually invented this mathematical model. All right, so he has this spreadsheet out there. I basically took the spreadsheet and modified it to fit some of the needs that we had. Added some macros to it, made some changes, but this is what the spreadsheet that I created looks like with some changes. And if you look at it here, you see there's a number here where you see you have your A and B. The only reason why we have this is because in Excel has a limitation where it has something wrong. It cannot correctly fit rational numbers. So to be able to do the linear regression in Excel, we have to go through these steps that you're seeing here to basically get an A and B number that we can convert it to alpha and beta. If you were using R or Studio, this would happen instantaneously. You wouldn't have to do these steps. But seeing that we're using a simpler tool, Excel, which I know most folks have, or OpenOffice, I'm going to show you this example here. So you look at this, basically we have our measurements, we do a bunch of analysis just to get these 2 points, and you see here where you have alpha and beta, and the only way you can actually make sense of this, just think of it like this. Those numbers come out as a ratio, so it's between 0 and 1. 1 being basically 100%, 0 being 0. So to quantify it mentally, just think of it, you always multiply this number by 100. So if it's 0.28 by 100, you get 28%. All right, and that's how you actually look at these numbers in terms of contention and coherency. All right, so this is what the full-fledged spreadsheet looks like. It shows you what you measured or what you got from production. It shows you what the model actually predicts your work rate at that amount of scale would be. So at 20 nodes, it's predicting you'll be able to handle X number of transactions per second. All right, and that's what you want to know. You want to be able to know what that's going to be like past what you can simulate or test. All right, and that nice little color chart you see, that color drop down you see on the right, literally what that tells you is visually it shows you after a certain point, literally what are you getting in return. So you see green, it looks great, 97%, you're getting 94, 91. That basically tells you as you add scale to the system, what you're getting back in return in terms of efficiency. So when you start seeing yellow, you're saying I'm only getting 67% of the scale I'm adding to the system. That's getting a little bit expensive. You look further along, you get down in the 40s, you start seeing the color red. That's telling you, hey, now I'm adding nodes, I'm adding virtual machines, I'm adding CPUs, and it's becoming expensive. I'm not getting the increase or improvement in capacity that I'm expecting, right? This is why you do this, because you want to know, what is this going to cost me? And for those of you guys who are into operations and infrastructure, you want to know this, because this is going to basically let you know whether it's a $15 million budget for supporting X number of customers or 5, which is very important. So this is why you want to know this stuff. And a lot of times, most companies are not going to invest in building out what I call it an elaborate performance test or simulation environment like Netflix does or some other places. They're going to tell you, no, you're going to have to figure it out another way. This is how you do it. So this is the second service that I showed you. Similar, different characteristics, but general, same chart. So let's move forward a little bit. You guys might ask, how do I know what throughput number to plug into this particular equation? How do I know this? And you've seen this chart. This is a basic load test chart. You ramp up, you maintain a load for a brief period of time, 20, 30 minutes, you ramp down, all right? And you need to take measurements at steady state. That top part of your curve is steady state. Basically, you take those measurements, you take an average or normalize them, and that's what you plug in for that. At 1 node, I get X number of transactions per second. At 2, I get another number of transactions per second. This is how you get that number. So you would simulate 1, what's the transactions per second? I add another node, what does that mean? I add 2 more, and so on and so on and so on. All right, so that's how you get that number that I pointed out as what I consider throughput, your work rate. And you might ask, well, okay, I got that. How do I determine how many nodes should I test? How many data points should I get? And when you look at this, basically what this tells you is, based on your sample size, what your error rate may be, right? And this is not a silver bullet. This is something that gives you guidance in terms of making a decision. So for example, say you launched a new product and you're only going to have maybe a small sample size of your customer base on it, say 400 or 1,000, right? Do you really need to go and do testing on 100 nodes or 100 instances of that service or that system? No, you don't. 6 is fine, because at that scale, the cost of actually the infrastructure is minuscule. There's no impact. But say you're going to launch this on 5 million. You're going to have 5 million customers use this. You might want to spend a little bit more time getting more data points, because that could, like I said, that could be the difference between you realizing that you need to spend $15 million or 5. And you want to get that right, because now you're talking money, a lot of money. So you want to be able to, if you're the guy in development and your guys are doing this exercise, you want to go to operations, you want to say, well, hey, we're going to need to have to basically budget for provisioning 2,000 nodes for this particular application. So that guy could go and talk to, whether he's using Amazon or if it's a private cloud, and decide, well, we need to go buy a bunch more blades because we need to add capacity in our data center to support this, right? So that's why you're doing this. So basically, the dev guys, it's important to them, so they know how the application scale, how it behaves. And for operations, it's important because now they understand their budgets, what they need to basically provide for you as a client, right? So now, a lot of you guys might ask, how do I know this thing is precise? How do I know that what this thing tells me is actually going to help me, hit the bullseye? And I'm going to show you an exercise that's going to basically do 2 things. It's going to show you the difference between precision and accuracy, and it's going to show you why one or the other is important. All right, so what you see in here, simple chart with some measured data. Right, you have throughput on your vertical axis, and we know what that is. It's a work rate. We have scale at the bottom, and that for you guys could be anything. CPU, number of servers, nodes. In this case, we're gonna focus on application nodes. So measured points here, I have 10 data points. And what I'm gonna do, I'm gonna apply this model using 6 through 10. So we're gonna see a first line that's gonna say, all right, I applied the model with only 6 of those data points and see how it fits to this real data. You see here, it goes through most of the data points, looks fairly accurate and precise, right? Tells me where the application is gonna fall over, good. I had 7 data points, and you see 7 data points in the first 4 of 5 data points fit fairly close to 6. They're starting to not be as precise at the top point at the tail end. So okay, a little bit of deviation, but generally close. We had 7 data points, and you start seeing there's some precision difference at the tail end of those curves, but they're fitting fairly close in the first 4 data points. We had 9 data points, you see the same behavior. 10 data points here in red, you see the same behavior. So now you're looking at this, and you see, well, the numbers seem to deviate a bit. The model projects what the system's going to do, but the projection deviates based on the number of data points. How do I know this stuff is right? And so you look at this. If you look at all of these lines, you see that these lines peak. The peak point at all of these lines intersect somewhere at a very small range of numbers. So basically this number, say this, let's hypothetically say this 10 virtual nodes right here. All of these curves intersect basically at this point, right? Now, that's the difference between precision and accuracy. Precision is these lines all being nice and matched up and on top of each other, nice. Accuracy is this part, which is what you care about. Because if you think about it, at this point, your system's shit in the can. You don't care. You are up, it's 2 in the morning, and your customers can't get served at this point. But here, you still have a chance. And this is why you want to make that distinction. Don't do this thing that I know a lot of folks kind of think, I need to put everything. It has to be absolutely right. No, it don't. It's the old agile term, YAGNI. Don't throw the kitchen sink at it because you're not going to need it. You ain't going to need it. So use as much data point as you need to get what you need out of it and get enough data that you can make a decision. Don't go and get hung up on these lines don't match up, because do the engineering analysis. If you think about it, like I said, you don't care, because at that point, you're in trouble. You care about the first half of this, all right? So I'm also going to show you now, how do you use this thing to actually track the way your service does release to release to release, right? So here, similar chart, you've seen this curve. You look at it, we have throughput over scale. Once again, scale is what? Servers, virtual nodes, CPUs, whatever. Throughput, work done over time. Here, you see we have alpha and beta, and in this case, you notice it's done in percentage. So literally what I did, I took what the actual value of alpha is, and if you multiply it by 100, you get the percentage, which is what you're interested in. And if you see here, we are having really high contention. It's 12.8%. That's really bad. That means this service is basically bottlenecking on something behind it. And if you look at coherency, it means the cluster is working very efficient. They're not losing a lot of efficiency by just keeping consistent, so that's great. So here, we saw this. I go to the development manager and I say, hey man, I think I know what this is, but I want you to do the analysis and tell me what's going on here, right? So he goes and says, all right, we're going to take a look at this. They dug into it and they realized, hey, we were doing something with our cache that was basically giving us about, say, a 30% cache hit, which is bad. So basically what was happening, we were bottlenecking on the database. So they made some changes and he comes back and says, hey, do the analysis again, check it out, tell me what happens. This is what happened. The service got like a 3 times improvement in terms of capacity or scale, right? But you look at the contention number for alpha, it's 3 times smaller than the first release. You notice coherency really didn't change much, right? The cluster works fine. But the parts of the application that were relying on the database, you can tell that the developers did some work because when you do the analysis, you do the math without them actually saying, I did a change to the database. You can tell, all right? And this is what this gives you as a performance engineer or somebody that needs to do capacity planning. You can now take this back to the development manager and go, this looks good. I think what you did here, basically they gave you a 3 times improvement in terms of capacity on that particular application. What does that mean? 5 million versus 15 million. That's big, all right? And this was a real service, not made up. This was a real analysis done, all right? So this is how you can use this thing to track release to release. And you can quantify it by those 2 numbers that what affects the shape of these curves, all right? And the reason why I say contention is very important in the beginning, because it basically affects the first half of this curve. Coherency is important because it'll tell you whether or not you're going to collapse on yourself or you're just going to sustain that. So basically mean, as I add more, am I going to do harm or not? Because doing harm could mean that basically you could saturate the damn database server, your connection pool is too much, and the database server processes just tank, which is worse than it hits a point where it just does not serve anymore, but it maintains what it has. That's the difference between am I going to do harm or not, which is why you also need to pay attention to your coherency number, because that's going to tell you the shape of this part of the curve, which determines basically, does the system collapse on itself when I add more, or it'll just stay basically 20 is 20, it stays there, and that's as much as it's going to give you. Versus if you add more, not only am I topping out at 20, now I'm going to give you 19, 18, and it gets worse and worse. So this is why you pay attention to this. So we've talked about the universal scalability law. We've gone through some examples as to how you use it, what the parameters mean, how you can apply it to a service to some extent, a single service. So now we're going to go into a real example as to how you apply this to a larger system. All right, so you've seen this before. Simple NT architecture. We know we can do modeling on this. We know we can do capacity planning on this. Complex system, virtualized, private, public cloud. Can you do this? Yes, we know that. So you see this. We had an application, or let me rephrase that. We have a system that brand new. We were trying to figure out, how does this thing scale? What do we need to do to figure out, can this support X number of customers that we want to put on it? So we tried to say, let's just try and model this thing as a whole and see what we can get. And we attempted that and failed, right? But we had some learnings from that. We kind of realized what we needed to do was to do this like we do software, modularize. So we decompose the system into its simpler parts. So if a particular service group did metadata, let's apply analysis to that. If a particular service was a client side, let's apply it there, right? Because we know how a system works. We know how we put the system together, right? Secondly, decompose the workflow. So for example, say if you look at 1,000 transactions going into the system, you know that downstream what the impact is going to be. This group of services are going to get 100 out of that 1,000, another one's going to get 300, and another group's going to get 600, just to simplify the example, right? So you got to decompose your workflow. And if this is your system, you know the way it works, or at least someone does. Whether it's an ops guy or a dev guy, someone knows how the system works, right? So if you look at this, you pick one group of your system that you've decomposed and you apply this model to it. So you know how that thing scales by itself. You pick another group and you apply a model to it. Next group, you do the same thing. And you can see here, each group of service here, these services actually have a different scaling characteristics. The curves are different. They look different. They have different alphas and beta, which is what you want to know. Because if you don't know how your individual parts perform or how they scale, then how are you going to know where you need to fix? How are you going to know bottleneck? And that's the point you're looking at. You're trying to figure out which one of these guys I need to fix first. Because as you fix that guy, he's no longer the bottleneck, then you work on the next part and the next part, and as a whole, your entire infrastructure does this in terms of scale, which is what you want. But you can't tackle it as a whole, you want to break it down into simple components, all right? So, how do you tie all of this stuff together, right? You've now figured out how application 1 does, you figured out the way application 2 works, you figured out application 3, you know application 4 needs 200 nodes, blah, blah, blah. You know, you figured all of that stuff out, all right? So, what do? You tie this stuff into a matrix, all right? And what's a matrix? It's an Excel sheet that you put some macros in, and you give it basically, here are all my applications. This is how this application scale. I can only get up to 20 nodes in this application. This is how my other applications scale. I can only do 12 nodes or 100. And you start tying this stuff together to kind of figure out how does this system as a whole actually work, all right? So you model the service 5. We're just picking this as an example, all right? You model service 5 and you say, oh, okay, I know service 5, I can support X number of customers. And you apply this approach to every single logical group of services in your system, all right? And once you do that, well, what this basically gives you is a picture of what your system looks like. It's going to tell you that, oh, well, I have 100 of these guys, and when I look at it, I can tell that as a whole, I can only support, say, 20,000 customers. But I realize if I went in and fixed service 5 and increased its capacity or its scale, I'll be able to support double that. Because as you fix different parts of your system, you're starting to realize that as a whole, the capacity of your system goes up, right? Which is why you're doing this. So don't try to model the whole system as a big monolith. Decompose the system into a simple component, logically. Decompose your workflow so that you get a better idea as to how the downstream impact actually works, right? So, for example, in our case, we do TV, right? That's big part of our business, television. We have lots of clients. And you want to know if a client wants to watch a particular movie, there's a couple steps that happen there. You log in, you search for content, you find something you want to look at, you play it, right? That in itself, there is a workflow, but behind the scenes, there's tons of stuff that happens, right? There's authentication, right? There's DRM that happens. There's CDN. The CDN comes into play, right? There's their entitlements. So now, we are the engineers, we are the architects, we know how the system works, right? So it's our job to actually now do the engineering analysis, you know, tie this stuff together, pull everything together, and that's where that part of it comes in. So don't think of the modeling tool as a silver bullet, it's a tool. That's exactly what it is, something you put in your tool belt that's gonna let you solve the big problem, which is capacity planning, right? So we know how each of these little buckets scale by themselves. We can figure out how many nodes we can put in production at maximum. We know what the throughput rate of each service group is. And at the end, you kind of figure out, well, I now know what the worst offending service is. And what do? You go back to the development teams, you fix this service, all right? Once you fix that service, what's going to happen? Another service is going to bubble up as a bottleneck. Right? And what do? You go back and you fix that service. And like I said before, it's a loop. As you fix each bottleneck in your system, another bottleneck arises, and you fix that. And like I said, what you'll see, your system as a whole, in terms of its performance, is going to improve, right? So this was done in Excel. I actually omitted the real data because of proprietary reasons, but this can be done in Excel. I did this in Excel to make it simple. And you're going to ask me, why is it important? So what's the big deal here? So those of you guys who've been in the Comcast market, you've probably seen this commercial for the new X1 platform. So what I just showed you is the approach, the technique, the tools we use to actually do capacity planning for this thing. All right? This was done, cloud infrastructure, the whole works. So it is real, it's something legit, it's something you can do in your environment, it's something you can take back, and basically I could say you can make it rain with stuff like this. You can do capacity planning. You don't need a PhD in that, it doesn't need to take 4 months. You can do this thing in 2 weeks at an agile pace, all right? And basically, let's recap. What do you learn here today? You can model simple and complex architectures using simple tools at an agile pace. That's what you learn here today. And any of you guys have questions, feel free to ask. I'm going to open up the floor. This is my Twitter tag, and I'm done. Yes. Yes, it was actually, we actually did that. And let me explain. The reason why I chose to use the server count, the instance count for a service, is because when you apply this model, one thing that I didn't mention, but it's in the book when you read the book, and just to make sure that everyone gets that, there's a quick reading list here. So Guerrilla Capacity Planning, that's the book if you want to check out. Basically, it describes this whole model. So one key thing about the model, you need to be able to either guess or your scale at 1. So it's, instead of guessing, I could measure that. So I just use one server node and use that number. Some other folks, they'll use like CPUs, or they'll use virtual users if you're using load runner. In my case, I didn't want to have to guess 1, because if you can get 1, the rest of your model is very accurate. So that's why I decided, spin up one service, one node, test it, measure it, do the analysis, spin up 2, do the same thing, and so on and so on and so on.
So you may have just answered this, but does it matter, so your measurements, does it matter where on the curve they end up? So like you have 4 measurements sort of like on the ramp up part, and that's all you can get.
Yeah, it's not that. So the key is this. If your measurements, if you do a good job measuring, the projection that you get, that nice curvy line, is going to be more accurate in terms of where it tells you. And mind you, there is an error bound, all right? So you will be off a bit. But if you only have 4 data points, then use it. But you need at least 4. You shouldn't go lower than that. Actually, I would recommend at least 6. But if you have 4, use it.
So my question was, though, if they are all on, like, sort of the, before contention takes over, like, does that matter?
Not really. Not really. That's the whole point of it. It tells you beyond where you can actually simulate. Okay. Next.
Have you looked at also testing or measuring servers when they're in a degraded state? So often you have a sort of clustered system that has to do more data replication or recovery when there were failed nodes.
So that's a good. So that's a good question. So something you have to keep in mind when you do this. The idea here is when you take that measurement that I consider that steady state, the idea is at that point, the service, how should I put it, the rate at what it's servicing the request needs to be fairly stable. It can't be fluctuating a lot, otherwise it's going to skew your numbers, right? So you have to be careful if you try to use measurements when the system's in a degraded state, because when it's at that point, it's not stable. So if your service, if it hits its maximum, it's going to fail fast. So 200, once it gets there, it's going to always serve 200, no more, but it will serve that 200. Then you have a number. But if your service is one of those services that when you get to 200 and you keep pumping more, it's not going to stay at 200, it's going to drop to 100 or 98 transactions per second. You want to be able to stop at that point and take that measurement and make sure you can sustain it. So think of it like this. When you pick steady state, it needs to be a sustainable work rate, no spikes. It needs to be sustainable, and that's why you pick that number. So do not measure where your system is actually fluctuating a lot in terms of work rate, all right?
I understand that, but that presents a challenge to treating something like a NoSQL cluster where you have some nodes that also are doing something different.
So this thing with this, right, is this. You're talking about multiple work rates?
Yes.
So in this case, when you're applying models, it's okay to average your work rates when you're doing this model at this level, because it's universal. Now, if you're applying Q in theory to it, you want to separate that out. So for this, it's okay to take multiple work rates and normalize them. If you're, like I'll tell you this, because I've done this exercise, if you're going to apply Q in theory at that low level, you want to break your work rates out individually, because it's going to complicate that. But for this, you can do normalizing and use more of an average at a higher level, because it's meant to be more of a universal projection, not specifically tell you, well, that transaction right there, the server can only support X number of that. It's meant to be more of a higher level system overall modeling approach. Not Q. If you want to do that, you would probably want to use more Q in theory for that, which lets you do more specific work rate type projections. Any more questions? All right, thank you.